assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
In this example, we take a conductive loop of wire, and initially it's in a region where there is no magnetic field, and we pull it into a region where there is a constant uniform magnetic field that is pointing parallel to the direction of the normal of the surface. So there's no angle between the normal of the surface and the magnetic field. And given that 8.87 times 10 to the minus 3 coulombs of charge is induced to flow in our loop, when we do this, we want to figure out what the strength of the magnetic field must be. Now we're also given all these other parameters of our loop setup here. That is the resistance of the wire in total, the area of the loop, and the number of turns. Okay, so the place we're going to start is with Faraday's law of induction, which relates the induced EMF to the change in flux over time. And the change in flux in this situation is just going to be the final flux minus the initial flux. And we can recall that the magnetic flux for a constant uniform magnetic field is just going to be B times A times the cosine of the angle between the magnetic field and the normal surface normal of our flat loop here. And in this case, that angle is just going to be 0 since they're parallel. So the flux is just BA for this example. And initially, our flux is going to be 0, right? Because we start off in a region where there's no field at all. And so our final flux is just going to be, the strength of the field times A, BA. So if we substitute that into Faraday's law, we'll have that the induced EMF is equal to minus BA divided by delta T. Okay. So we're trying to solve for B, right? However, we don't know what delta T is still. We don't know in what period of time this loop is brought into this field. So we're going to have to work around that some other way. We also don't know what the induced EMF is, so maybe we can deal with that at the same time we deal with delta T here. What we do know is that the induced EMF is going to be related to the resistance of our wire by Ohm's law. So Ohm's law states that the voltage drop across a resistor is related to the current flowing through it, E equals IR. And our voltage in this case is just our induced EMF. So we have E equals IR. Now the I in this E equals IR, the current, we know to be as a charge per amount of time, right? So we can write this just as Q over delta T. So if we substitute that in, we'll have Q times R over delta T. So if we substitute this into our Faraday's law over here, we'll have Q times R over delta T is equal to minus E times A over delta T. And since we're only looking at the magnitude of the field here, we can actually just right now get rid of our sign here and say we're looking for the magnitude of the induced EMF, and therefore the magnitude of our field. And A and delta T will always be positive, so we don't need to put magnitude signs around those. Okay. Magnitude of B and Q is positive. Cool, everything's good to go. So our delta T's are actually going to cancel out, and we can see that we don't have to know them at all. So now we're in a situation where we can just solve for B and call it a day. Now, the one thing we neglected to leave out here was that we worked all of this out for a single turn of our coil here, but we actually have 1,850 coils. So we could have tagged that on in our flux here as N times B times A, or we could have put it in front of Faraday's law and had N times the change in flux over the change in time. So I'll tag it on the flux, and then we'll just make sure that it follows through in the rest of our equations here. So we should have an N times B times A here, and finally over here an N times B times A. All right. So now we're going to solve for B. So we'll just divide both sides of our equation over there by N and A. So we have N times A times B, divide by NA. And we will just end up with B equals QR over N times A. Okay, and these are all things we know now. We have the charge, the resistance, the area, and the number of turns. So all that's left to do is just plug in our values. And if we do that, we're going to get that the magnitude of our magnetic field is just 0.46 Tesla. So there you have it. We just determined the strength of our magnetic field. When we pull it in from no magnetic field to a constant uniform magnetic field, given that we know how much charge ends up being induced into the loop.